Okay, so we've talked about coupon collecting, and now we're going to do another example that involves coupon collecting, which is in the context of the distribution of a length of a game in craps. So remember, we've talked previously about how craps works. So remember, the rules in craps is that there's an initial come out roll. And then the come out roll establishes the point. Well, assuming that, so if it's a 2, 3, or 12, the game's over and the player loses. If it's a 7 or 11, the game's over and the player wins. And anything else becomes established as the point: 4, 5, 6, 8, 9, or 10. Once the point is established, we continue then rolling until either the point is re-rolled or a 7 is rolled, and then the game ends. So let's let R be the total number of rolls. And A be the number of additional rolls after the first roll. If any. So we're going to condition on the first roll. And if the first roll ends the game, then value of R is going to be 1. Otherwise, we continue and we have to figure out how many additional rolls are needed. So R is equal to the first roll plus the number of additional rolls, meaning that the expectation of R is 1 plus the expectation of A. And the standard deviation of R is equal to the standard deviation of A. For the different possibilities of the first roll, there is each of the possible sums from 2 up to 12. Remember, we've defined the event Tj that the first roll is a sum of J. And the probability mass function of this random variable is called the triangular distribution, which assigns probably 136 to 2, 236 to 3, 336 to 4, up until a maximum of 6/36 for rolling a 7, and then we come back down linearly until probability of a 1/36 is probability of a 12 is 1/36. So for n equal to 0, we want to calculate, well, what's the probability that A is equal to n? Well, the probability that A is equal to 0 is just the probability that the game ends on the first roll. That is, we need to roll craps 2, 3, or 11, or 2, 3, or 12, or we have to roll 7 or 11, a winner. And so we can calculate that as 1/3 if we add up the probabilities. For every other value of n, we need to condition on the first roll. So the probability that A is equal to n is equal to sum over the possible outcomes of the first roll that lead us to keep rolling, right? Law of total probability that A is equal to n, given that the first roll is a J, times the probability that the first roll is a J. And So we know these probabilities, and now the question is, well, what are these probabilities? Well, how do we think about this? Well, this is the probability that the number of additional rolls needed is n, given that the point is j, right? Distribution. So it's a conditional probability of number of additional rolls given that the point is j. Now, if the point is j, what happens is we're going to roll until we either hit a j or a 7, right? So the number of additional rolls is geometric, and a success, even though we might win or lose, we might lose if we roll a 7 out. A success is just ending the game in this example, right? So we want to know how long does it take to end the game? Well, the probability of the game ending on any given roll is P sub j plus P sub 7. Everything else is going to keep the game going. So it's a geometric Pj plus P7 random variable. So if we write theta sub j equal to Pj plus P7, then we can write the probability that A equals n is the sum j equals 4, 5, 6, 8, 9, or 10. Pj, that's the probability of Tj, times 1 minus theta j to the n minus 1 times theta j. That's the distribution of A. And to find expectation of A, right, one thing that we can do is we can use the law of total probability on expectation. This is using the idea of conditional expectation. We'll get to in a bit more detail, but intuitively, it's if we roll a j, that does change the nature of the random variable A, and the expectation changes because the distribution of A changes, and the expectation of A given Tj is going to be the expectation of geometric theta j. Well, we know what the expectation of geometric theta j is. It's 1 over theta j. And so what we're left with is this is twice the sum j equals 4, 5, or 6 of Pj over theta j. Theta j is Pj plus P7. And we can do this math to calculate that the expected length of a game is 392 over 165. So it's actually pretty short in general. It's less than 3 rolls, about 2.5 rolls, but that's the exact value. Okay, but that's again how we would use law of total probability, conditioning on the first step, and geometric distributions to answer a question. It's a bit more of a complex question. It's not as simple as saying the outcome that we want, the number of rolls R, is exactly equal to is exactly a geometric random variable, but instead it does require quite a bit more. It does require quite a little bit more thinking, but all the pieces are there. We just have to put the pieces together.